The chi-squared test for homogeneity of proportions is the last of the chi-squared tests that we're going to look at in our course. This test is supposed to be used when you are trying to find whether two or more populations have the same proportion of individuals with some characteristic of interest in them. And it sounds so glib to say that, oh yeah, when you have more than one population, you're supposed to use chi-squared homogeneity of proportions. But in practice, it can be a little bit confusing when you actually have more than one population. Let's look at a couple of quick examples in the text, and then we'll get to the main example that we're going to look at in this video here. One of the problems, which is a good example, is on the screen in front of you right here. It's number 15. And you can read it for yourself. But they're sort of leading you with part A of the question when it says, explain why this data should be analyzed by homogeneity of proportions. And so, of course, the pat answer there would be, well, you have more than one population. But if you look, you have Democrats and independents and Republicans. And is that really three different populations? I mean, that's a fair question. I mean, they're all Americans, are they not? And so it can be very subtle when you have more than one population. And we're not expecting you to be an expert in a single section of a text, but we're trying to get you to think about this. And so I would say that it makes more sense to run homogeneity of proportions for this problem than it would, say, independence, because we're not really looking at levels of a variable. You understand? Like, for example, the political party that a person tends to lean toward or affiliate with is not like a level of a variable. And so you could say, well, in that case, it would make more sense to test it as a homogeneity of proportions. It's the same process, right? We're still using a chi-squared test, as you're going to see, and so on. And there are some other examples that are worth looking at as well. So look at that one there, number 15, and then look at this one as well. Look at number 16 at the bottom of the page there. The title is a hint, or they're sort of telegraphing the fact that this is a continuation of the same line of thinking. And the data set is given on the next page, as you can see right here. And so again, you're talking about individuals with three different political affiliations and different views of something. And so you can make the case that it makes more sense to test this as homogeneity of proportions than it would, say, as independence. And so one way you can arrive at the fact that you have multiple populations is a process of elimination. You're sort of asking yourself, are these levels of the same variable, or are they in fact different populations? That's really the distinction that we're making here. Now, for this video, we're not going to do either of those problems. We have a prepared example from the text that we're going to work on, and so that's because, well, there's a couple of reasons we want to do that. First of all, it makes it much easier to follow along the first time, and second of all, it affords me the opportunity to show you sort of a different way of going about the test. So I'm going to show you two ways to do the test, and you can choose whichever is best for you. It's up to you, whichever seems the best to you. Anyway, let's take a look at our example. You can see the very start of our example down at the bottom there, but before we get to that, you'll notice there's a paragraph here, a couple of paragraphs actually, which are very good to read. And since you're allowed a sheet of notes when you write the exam, it may not be a bad idea to put your own paraphrased version of this down there. Notice that it's saying, so if you have a single population in which two variables are measured on each individual to assess whether one variable might be associated with the other, conduct a test of independence. If you have two or more populations, blah, blah, blah. That's what we're trying to get you to recognize. Anyway, here's our example. So in this case, it is a prepared example in the text. You might think to yourself, how would I know, apart from the fact that the book is telling me that this is in fact a test of homogeneity of proportions and not independence? And I think a reasonable response to that would be, well, if you look what's in the contingency table here, you'll notice that we have three different treatments that are being given to individuals. So one of the groups of individuals is receiving Zocor, which is a cholesterol drug. Another group is getting a placebo, and a third group is getting some other cholesterol drug. And so it's not like we're giving everyone Zocor and they're just getting different dosages or something like that. We have 3 different treatments. And so that's why it doesn't make sense to treat this as independence, because we're not looking at levels of a variable like dosages of Zocor. We're looking at Zocor versus placebo versus some other drug. And so that makes most sense to treat it as homogeneity of proportions. So in other words, we're treating the Zocor, the people who receive Zocor as one population, the people who receive the placebo as another, and finally the third group, the ones that receive the other cholesterol drug, as the third population. So we have 3 populations here that we're comparing. Now, you know that for this type of a test, we end up using the matrices in the calculator. That's the easiest way by far. If you don't like using the matrices, that's fine. I'll show you a different way at the end, and you can use that way. You can use whichever way seems good to you. I don't have a dog in that fight. So anyway, notice for this particular contingency table here that there are no marginal distributions. So if you were actually working this problem out, say on an exam or something like that, that would probably be your first step, would be to get the marginal distributions. In other words, the column sums and the row sums. But if you're reading along, getting this from your text, you realize that the very next page has that information already, and so we might as well just get it. So in this table 13 here, this version of the contingency table, they've supplied us with the marginal distributions, and so this permits us to then key that into the calculator. So if you'd like to follow along, feel free. You can pause the video, and you can also get the information directly from your text. Anyway, let's walk through the test on the calculator, see how it's going to look. So for entering the data, if you recall, the chi-squared test is going to be using the matrices, which you access by pressing second X inverse. That takes you to the matrix submenu, and we're going to edit matrix A for the observed counts and matrix B for the expected counts. And so if you go back and look at the contingency table, we have 2 rows and 3 columns. And so as far as the size is concerned, matrix A should be 2 by 3. And we're then ready to key in those observed counts. Join me if you would. Okay, so I have my observed counts in there, and I'm ready to key in my expected counts. You need to quit this, go back to the matrix menu, go back to the edit submenu, and then you're going to edit matrix B, and it has to be the same size. So matrix B would be 2 by 3 as well. And if you recall, there's a formula we use. We're going to take the row total times the column total, and we're going to divide that by the grand total. And so those values are visible in the contingency table there. So for that first expected count, we're going to take 72 times 1583 and then divide that by 1919, and the rest of them in a similar fashion. And so you'll be able to see when you look back at the text that that matches what we have there. And so all those values match exactly with what we see in the text. And so at this point, we're ready to run the test. So you can quit this, and then you can go back to the stat menu, and you want to go to the test submenu, and we are looking for the chi-squared test, which on my calculator is letter C. It may be a different one on yours. When you press enter, you can see that we have observed and expected matrix A and matrix B as we knew, and then of course we're ready to calculate. And so there are exactly the values you see in the text. You have your test statistic as well as your p-value. And with a p-value that small, of course, we would be rejecting the null. And you can read that in the text. That's exactly what it says. Now, there is a different way to go about this. If you don't like using the matrices, I understand. Sometimes people don't. And so if you're comfortable testing goodness of fit, as we showed you using the lists, you're welcome to try this test in that way as well. The only thing about testing it using the list is you have to know how to calculate the degrees of freedom. And so you can see right here with this version of the test, the calculator is telling you, hey, I got 2 degrees of freedom. If you're going to use the lists and you're going to construct everything yourself, nothing wrong with that, but you have to know how to get the degrees of freedom. And so it's the number of columns minus 1 times the number of rows minus 1. And so in this case, 3 minus 1 is 2, 2 minus 1 is 1, and so 2 times 1 is 2. That's where we get the 2 degrees of freedom. You can also read about that in the text in the treatment there. Anyway, let's look at this other version of the test. If you prefer not to use the matrices, you can run the test in the same fashion that we did the goodness of fit test at that time, using the lists, in other words, as follows. You go to the stat menu, and for data-driven problems, you want to clear your lists. So I'm going to do that here. You're going to need a total of 4 lists, which is what I'm clearing for. And so that command has been run, and so then I can go about keying in my stuff. The one thing that can confuse people is you need to make sure that when you navigate the contingency table to use this version of the test, that you navigate it the same way both times. What I mean is, if you're going to go across the rows from left to right, then do that for both your observed and your expected counts. The calculator is assuming, or we are assuming rather, that when we run this test in this fashion, that the corresponding entries from the contingency table are at the same location in each list. So in other words, if you look at our contingency table for this problem here, as I key in my information to the calculator, I'll go from Zocor to placebo to the other drug, and then Zocor to placebo to the other drug. And I'll do that for both lists. I want to make sure that everything is in the right position. All right. So put my observed counts in list 1. And I will put my expected counts in list 2, and I'll calculate them the same way that I did when I was using the matrix. And there you go. List 3 is going to give us each of the contributions. So you go up to the top of the list like that. And if you recall the formula we're using the very same construction for the test statistic that you can see right here in front of you. And so we want to build each of the elements in list 3 in this way. So once again, I go up to the top of list 3 so that the name is inverted there, as you can see. And I'm going to open up a couple of parentheses. I'm going to take observed minus expected. I'm going to square that, and then I'm going to divide that quantity by the corresponding expected value. There you go. There's your individual contributions, and if you go back and look at what's in the text, you can see that they are exactly the same. And then we're going to build our test statistic here with this very last item. So you go up to the top of list 4, make sure it's lit up like that, and then you want to quit this, or well, actually, you want to go to second stat, which takes you to the list ops menu. You want to go to the ops submenu, and then you want number 6, which is the cumulative sum. And we are taking a cumulative sum of list 3. And so that very last value down at the bottom there, which has been conveniently rounded for you, it's 14.707. That will be our test statistic, and we are going to use that to get our p-value. Now, as an aside, if you don't like using the p-value, that's perfectly fine. I don't like to be the thought police on exams, and so as long as you have everything written up properly, if you want to use a rejection region method, that's perfectly acceptable. You just have to make sure you have enough detail down so that we can make sure you got it correct. Anyway, for obvious reasons, I prefer using the p-value. So I've got that value, 14.707. And if you remember, the degrees of freedom is the number of rows minus 1 times the number of columns minus 1. So 1 times 2 means 2 degrees of freedom. You want to quit this. You want to go to the distributions submenu. And again, we're here to get our p-value. And so we want number 8 on this list here, chi-squared CDF. And 14.707, as you can see right there. Upper limit is always positive infinity. If you've forgotten how to enter that, it's 1. And then scientific notation, 99. So that's the way you speak 1 times 10 to the 99 power to the calculator. And then everything is good to go. You can see the syntax of the command right there. So if you're using a TI-83, you're just going to type it in like that and then put the closing parenthesis. Press enter. And there's your p-value, just like before. And so you can see the result of the test written up in the textbook there. And I hope this has been helpful. If you have any questions, feel free to drop me a line. We do have another example of this on tap in the very next video.